Hi, chemistry students. So today we are looking at properties of gases. For the next 2 weeks, we'll be looking at gases. Right now we are starting with the kinetic molecular theory, and we'll get into our slideshow in just a second. But I wanted to show you this gas properties that we might look at later in the week. Um, but it's kind of fun. You can pump different types of gas into a box and watch as they interact. You could change the type of gas. So the like bluish purple is larger, it's a little heavier. The red is smaller, it's a little lighter. You can change the dimension of the box if you want, and you can heat it up and you can cool it down. All right, and you can observe all of these changes. So I'm going to reset it, and here's what I want to look at. All right, I want to do something. I want to add one particle of each species. All right, one of the heavy and one of the light. And the first thing I want to talk about, we should be able to see a pretty drastic thing going on here. The heavy species is moving faster. The lighter species, or excuse me, the heavy species is moving slower. The lighter species is moving faster. All right, they have the same kinetic energy. Kinetic energy is 1/2 mass times velocity squared. So if for them to have the same kinetic energy, the lighter particles get to move at a faster speed. All right, and the larger ones move at a slower speed. And that should be pretty logical, right? If you've ever played a sport, usually the really small players are the really quick, fast ones, right? I was always one of the larger guys. I moved a little bit slower. All right, now we're gonna wait till they collide. All right, so if we were in school, we would watch this video until they collide. If it took 40 minutes, then that's what it is, right? It's like that episode of The Office when they're waiting for the screensaver to hit the very corner. But we want to see a collision. Oh, that was so close. Because when we get the collision, we're going to be looking to see something happen. All right, the collision is what we're going to say elastic. So they're just going to bounce right off. Now, the red particle might start moving slower and the blue one might start moving faster or vice versa. It's okay if they change speeds, but the idea is no energy is lost in the collision. So when we say it's elastic, nothing's lost, and it's if one goes faster, the other goes slower or vice versa, they might go at the exact same speed. Now we do see them colliding with the walls a lot. Oh man, but I want to see them collide with each other. We were close. We almost had it. All right. You're probably thinking, Mr. L, are you really going to make a whole video just waiting for them to collide? Yes. Yes, I am. And you should watch the entire video. All right. It's riveting. I think we might get it. Oh, we got it. It collided. It did change the path when it collided, which is fine. The collisions will alter that. So let's do something else. Let's do so we'll put 50 of these large ones there. And let's heat it up a little bit. All right, let's get them moving a little faster. So the idea of the collisions is that these particles, they're just moving in straight lines until they hit something. And when they hit something, they bounce. When they hit the wall, they bounce off. All right. And now let's add one single, oop, one single red one. And we should be able to see all of the collisions that the red one, like if you just follow just the red ball, it's going to just get banged around between everything. So focus on the red one, and it moves slow and it moves fast and it changes directions and it's bouncing around and it just keeps getting hit by all those different particles. But it's an elastic collision. So this shows us the kinetic molecular theory really well. Let's move into our notes now. All right, so we are looking at the kinetic molecular theory of gases. You'll sometimes see it abbreviated as KMT. All right, so the idea is just like that simulator showed, the gases are going to be little particles and they're going to move in straight lines until they collide with something. And there's a couple of postulates of the kinetic molecular theory. When we say postulate, it's like the main points, right? So like we learned about the atomic theory, there was postulates of the atomic theory. These are the postulates of the kinetic molecular theory. All gases, particles are in constant and random motion. right? So they're moving in a straight line until they collide with something else. It is random motion. There's no logic behind the direction they move in, and they're always moving. There is no sources of attraction or repulsion among gas particles. They're so spread out that they don't attract each other and they don't repel from each other. All right, now this is a theory, and this is kind of making all the assumptions. There actually are for certain real gases, but we're kind of assuming it doesn't happen. So no attraction, no repulsions. The collision of these gas particles with an object results in gas pressure. And we're going to say all of those collisions are perfectly elastic. Now, again, I want you to think, are they actually perfectly elastic? Well, no, all right? But the idea of this theory is to simplify gases so we can make a little more sense of it. And the average kinetic energy of these gas particles is directly related to their absolute temperatures. And we've seen this. So higher temperature, faster moving particles, lower temperature, slower particles, right? So that's not new to us. So between these two pictures, I like the spacing on the picture on the left, but I like the arrows, right? We want to show the arrows to show every particle, it's in constant motion, it's in random motion. Not only are the gas particles spread out, but they're moving constantly and randomly. But they do move in straight lines until a collision causes their path to be changed. All right, now again, they're spread out. We do not want to see any attraction between molecules. All right, attraction is bad because it actually can like change their course. So now they don't move in that constant random motion, not exactly, right? Kind of slows it down. So we're assuming no attraction between molecules and also no repulsion, right? They don't push each other out of the way. They don't attract towards each other. They just move in constant straight lines until they make a collision. And those collisions, when we say perfectly elastic, that means no energy is lost. So imagine if you had a rubber ball and you drop it and you let it bounce on the ground. It never comes back up to its exact height. And with each bounce, it usually goes a little lower, right? Because it loses energy. That's how particles, that's how objects behave. But what we're assuming for these gases is that it's perfectly elastic, so it does not lose energy. So instead of going, lower and lower each time, it can bounce right back to the same height. So they can just keep moving randomly, unlimited, for as long as we want. And the collisions with the walls of a container create the pressure, right? So if they collide in something like this, where there's a movable piston, more collisions can push it upward, less collisions will push it right back down. Thinking about something like a balloon has the gas trapped inside, all right? So there's collisions happening inside the balloon. There's air pressure outside the balloon colliding, and the size of the balloon is based on how many collisions are happening inside, and it'll spread out if there's less collisions on the outside. We'll be looking at some of those relationships in the next video. All right, but just think collisions with the walls inside, collisions with the walls outside, and when they're equal, the balloon stays at a set volume. All right, which is why when you blow into a balloon, you can make it bigger. You put more air inside the balloon, so there's more collisions to be had. All right, and again, lower average kinetic energy, we're going to draw a shorter line. Higher average kinetic energy, which means higher temperature, longer lines. All right, so just hotter gases, they move faster. All right, now if they're moving faster, that means they can hit the walls more often. So they will create more pressure. Again, we'll see that in a later video. So this is the moment. Oh God, what do you mean it's not available? I was gonna play Queen's Under Pressure, but we can't get it. Again, this is another moment where we would play the entire song in class. It's a great song. All right, but we're gonna talk about pressure. So pressure is defined as the force over an area. All right, so that's like if you were to take physics, that's how we would define pressure. An elephant's foot actually generates less pressure than a woman wearing a stiletto high heel shoe. All right, even though the elephant is much larger, so it generates a greater force, its foot is wide, so it's a big force, but it's divided by a big area. The woman is significantly smaller than the elephant, so not as much force, but it's over a much smaller area. that stiletto heel. So it actually generates a lot of high pressure, and it would actually be better like if an elephant walked across a basketball court, right? The like a wooden basketball court that was just refinished, it wouldn't really damage it that much. Whereas if a woman wore high heels, they would actually mess up the court really bad. All right, now we're not going to use that formula. For us, pressure is purely the number of collisions. More collisions, more pressure. Less collisions, less pressure. All right, so here we have low pressure. We have kind of a wide cylinder. We have our pressure gauge. All right, and there's a certain amount of collisions with the container. Now, when we restrict the area, we make it much smaller, the volume, all right, those particles hit the walls more frequently, and so we get a pressure reading that's considerably higher. All right, so how do we read pressure? Anyone that's in auto, you've probably used one of these pressure gauges. All right, so you put it up to the tire valve, and it gives you a reading. What's going on inside of it? There's a spring. Now the rod itself is calibrated, and when you let the air in, it pushes a certain amount against the spring, right? The more collisions, the more it can push. The less collisions, the less it'll push against the spring. And then you can read the tire pressure, right? This little space of air will be the same as the tire, all right? That is like the pen pressure gauge. Usually we see it as a valve. You may have seen it on a bike pump, all right? And it's important. You should know your tire pressures, all right? So you're probably thinking a lot of the stuff you learn in chemistry, it's a lot of theory, you're not gonna use it. Tire pressure is something that you are absolutely going to use in the real world. You guys are all learning to drive. This is something that's important. The tire pressures are listed on the inside of the driver's side door, right? There's always a little chart. It's also in the owner's manual. I keep a pressure gauge in all of my cars, right? You never know when you're gonna have to check your tire pressure. Sometimes with my old truck, I come out of work and I see that it looks like this. It's laying pretty flat, and I check the tire pressure. I've had it down as low as 8 psi, and I was like, "Whoa, good thing I didn't drive home with that." I kept a tire pump in my car, you know, one that would plug into the console. So you should always check your tire pressure. Having either overinflated or underinflated tire pressure, you're going to get worse gas mileage, and it's going to just be generally more dangerous. You should always, no matter what car you drive, you should always have good tires on it. So do not skip on that. So that is my little PSI for the day. All right, several different units for tire pressure: the pascal, the bar, the kilopascal, the megapascal, the pound per square inch, kilograms per square centimeters, inches of mercury. Not listed here, millimeters of mercury, torr. Atmospheres. All right, so tons of pressure units. We're only going to use a certain number. All right, we're going to either use the atmosphere, which is abbreviated as ATM, pounds per square inch, which is PSI, kPa, which is kilopascals, or millimeters of mercury, which is mm of Hg. Sometimes you just see it as just mmHg. All right, up here, these are equivalences. 1 ATM is equivalent to 14.7 psi, is equivalent to 101.3 kPa, is equivalent to 760 mmHg. They're all equal to each other. All right, so 14.7 psi equals 760 mm of Hg. All right, the atmosphere is the unit we like the most, all right, because it's simple. 1 atmosphere is equal to the air pressure at sea level. All right, now we're pretty close to sea level, so what we are experiencing in this room is 1 atmosphere of pressure. That is equal to 14.7 pounds per square inch. This is a very common American unit. Cars are listed in PSI. So your tire pressure is probably about 35 PSI. Now, just think about something. Since 14.7 pounds per square inch equals 1 atmosphere, 35, that's a little more than double. So inside of a tire, it's a little more than 2 atmospheres. All right. For my bike, for example, the tire pressure on my bike needs to be between 90 and 100 psi. All right. So it's pretty high. So, you know, and again, if you're riding a bike, you want to make sure your tires are inflated to the same proper tire pressure as well, just as important as a car. All right. Now, the kPa, the kilopascal, This is a common SI unit. Remember the SI system, that System Internationale? This is going to be important if anyone goes on in the fields of engineering. A lot of things will be reported in KPA. Some foreign cars, I know certain Subarus, Japanese cars, they will list the tire pressure in KPA instead of PSI. So think about it. We said tire pressure 35 PSI, that's about double, a little more than 2 atmospheres. So that's a little more than 200 kPa. All right, some of those gauges, they'll say, you know, it should be 230 kPa, and you want to follow that. And the last one, the millimeters of mercury. All right, how did we initially measure pressure? All right, they used devices like this. They had a mercury-filled dish, they had a tube, and as the atmosphere pushed down on it, the mercury would creep up, and what they found is at 1 atmosphere of pressure, mercury could rise 760 millimeters. You'll also see inches of mercury, and that's just the conversion between millimeters and inches, but I like millimeter, that's the old school one. So we are going to see pressure conversions. So you want to remember our unit conversions is the unit you want, right, is going to be in blue, what you're changing into. The unit you have is here in red. I call that the given. So you take your given, you multiply it by the conversion factor for what you want, divide it by what you've been given. Remember, I've said this in the past. You use what you've been given to get what you want, and you prioritize what you want over what you've been given. All right, so we'll see an example here. Convert a pressure of 847 millimeters of mercury to kPa. Take your 847 millimeters of mercury, all right, and multiply it by what you want, kPa, so you put its equivalence, 101.3 kPa up top, divide it by what you already have, millimeters of mercury, use its equivalence, 760. All right, so you'll do 847 times 101.3, and then divide it by 760, and that gives you 113 kPa. All right, so here's your given. Identify the given unit, put the given unit on the bottom, put the unit you want up top, put in the equivalences. Right? Make sure you write them all down. They are important. 1 ATM, 14.7 PSI, 101.3 kPa, 760 mm of Hg. All right. What is 8.9 PSI expressed in ATM? Right? So again, we take the 8.9 PSI. That's our given unit. Given unit goes on the bottom, PSI on the bottom. What you want, ATM on top. Put in their equivalences, 1 ATM, 14.7 PSI. So this means 8.9 times 1 divided by 14.7, 0.61 atmospheres. All right, here's another 2 examples. Convert 613 millimeters mercury to ATM. Convert 613 millimeters mercury to kPa. This is the setup. You're always multiplying by a fraction. All right, unit you want always on top. And where do I get these numbers from? These equivalences will not change. All right, so just make sure you have them down. All right, so that's pretty much it for the kinetic molecular theory. It is how to view gases at that atomic, at that molecular level. They're moving in random motion. The collisions with the walls create the pressure. The higher the temperature, the faster the particles move. The lower the temperature, the slower they move. And we will see how that affects us in some mathematical relationships in the next videos.